Section 7.2 is on Law of Cosines. So we looked at 7.1, which was dealing with Law of Sines. And now we're going to switch to those cases in which you have to use your Law of Cosines. So the Law of Cosines are listed at the top of the page there for each side. So if you were solving for side A, you would use the first case. If you were solving for side B, you would use the second case, and so on, side C. Before we go on into an example, let me also note that each one of these formulas can also be solved for the angle. So this can also be used to find an angle A, B, or C, depending on which one you're looking for. And let me just kind of show you with one of them. I'm not going to do it for all three of them, but let me show you with one of them how I can. Let me take the first one and solve for cosine of A. So if A squared is equal to B squared plus C squared minus 2 times B times C times cosine of A, angle A, and I want to solve that for angle A, which would be a case where if I know all three sides and I'm trying to find an angle, that would be a time I'd want to use this. So, it'd be like a side case. So if I subtract the B squared over and the C squared over, okay, I can just subtract those from both sides, move them to the other side. And at this point, this is multiplication, negative 2 times B times C times the cosine of angle A. So if I want to undo multiplication, I would divide. I'm trying to isolate angle A, so I'm going to start by isolating the cosine of A. And so now I would divide both sides by negative 2 times B times C. And at this point, I'm going to go ahead and write the cosine over here. Cosine of angle A is equal to A squared minus B squared minus C squared divided by negative 2BC. And then, of course, to go ahead and find angle A, you would have to inverse cosine. Remember that this number right here would have to be less than 1 because cosine can't be greater than 1, because basically if it is, the hypotenuse or the adjacent side is longer than the hypotenuse, and that can't be true. Okay, so again, if you're solving for a side, you'd want to use one of these. If you're solving for the angle, you would want to use it in this form. Okay. All right, let's go on into example 1. So this example says to find all the missing parts of triangle A if they're giving us angle A, side B, and side C. So basically, let's draw it here. We have triangle ABC, where angle A is 48 degrees. I don't know angle B, and I don't know angle C. Side B, which is always across from angle B, is 15 inches. So this is 15 inches here. And side C, which is across from angle C, is 25 inches. All right, and so we're trying to solve the triangle, which means that we are trying to find all. They're giving us 3 parts, and we're trying to find the other 3. So I need to find angle B and angle C, and then side A to be able to solve this triangle. All right, so let's start, since what we have here is a case of side, angle, side, which is, of course, one of our, if you go back to the 7.1 notes from the table at the beginning, it showed you what cases you would use law of cosines for, and so side, angle, side was one of those, and so was side, side, side. So this is this case of side, angle, side. We know the 2 sides and the angle between them. All right, and so I am looking for side A, so I would apply the first formula right here. I know the side B, I know the side C, and I know the angle A. So I've got everything I needed to be able to crank through that formula, and it's just really more of a plug substitution, plug and chug, put the numbers in, work it out. All right, so A squared is equal to B squared, which is 15, plus C squared, which is 25, minus 2 times 15 times 25, times the cosine of angle A, which is 48 degrees. Literally would probably just type that in my calculator here, and crank out an answer. Okay, as I was looking for my calculator in the last part of the problem, I had to pause the video to find my calculator, and then I thought I hit the video start button and I worked the problem and had not hit it. So instead of redoing the whole thing, I'm just going to kind of walk through and talk through what I did. So at this point where I left off, I basically just typed this in my calculator, and this is what I came up with. I had to solve for A, so I had to, A is going to be the square root of 348.15, which was 18.7 inches. So that's the length of side A. All right, next, in order to have solved the entire problem, at this point I didn't know angle C. I've just filled that in since I did this other part. So in order, I went ahead, I could either find angle C or B first. It didn't make any difference. I just chose B because I just had to pick one. And so notice the formula that I used to find cosine of B, and that comes straight from this. I just solved this for cosine of B, just like I did this one for cosine of A. So B squared, you're going to subtract over A squared and C squared. So cosine of B is going to equal B squared minus A squared minus C squared, and then divided by negative 2AC, and that isolates cosine of B. So that's where the formula comes from. And I simply just substituted in each side. I knew side B was 15. I knew side A was 18.7. That's what I had to find. I knew side C was 25. A is 18.7. C is 25 on the bottom. And I cranked this out, typed in my calculator, got 0.8018. So again, to solve for angle B, I have to inverse cosine. So B is going to be the inverse cosine of 0.8018, which was in degrees 36.7 degrees. So we went ahead and rounded to keep with significant digits here with the angles. We went ahead and rounded to 37 degrees. And then once I found those two angles, I didn't need to do another law of sines or cosines problem. I just used the 180-degree rule. I knew that 48 and 37 and angle C have to add up to 180. And so angle C has to be 95 degrees. In example 2, we're asked to find basically the shorter side of a parallelogram if we're given the lengths of the diagonals and we're given one of the angles at the intersection of the diagonals. So I'm going to draw this out. So a parallelogram does not have to have right angles or anything. But one thing from geometry you do have to remember to be able to work this problem, let me draw the diagonals in here, is that the diagonals in a parallelogram bisect each other. That was one of your properties of parallelograms that you learned in the quadrilateral unit in geometry. So if one diagonal is 28.2, and so since that's the smaller value, I'll put that on the smaller diagonal. Bisect means they split each other in half. So that means that half of 28.2 is on this side and half of it is on this side. Half of 28.2 is 14.1. So that half is 14.1 and that half is 14.1. And in the same way, this diagonal, which is 36.4, is cut in half by this diagonal. So this diagonal goes to the middle of this one, making this half 18.2, half of 36.4, and this half 18.2. The other information they give me is the angle at the intersection of the diagonals is 60.4. So, it's either this angle at 60.4 or this angle at 60.4. One of them is acute and one is obtuse, so it would make sense to let the smaller angle, the acute angle, be 60.4. Okay, and so the task is to find the shorter side of the parallelogram, which would be this side. All right, and so let me just kind of pull the little triangle out here. And so let's see, I'll just kind of draw it like it's laying there. Let's say this is, let's label it, it'll make it easier too. So let's call this A, B, C. And so we know the angle C here is 60.4 degrees. We know this side is 18.2. We know this side is 14.1. And we are trying to find side C. Okay. And so that's a side angle side case. We're going to use our law of cosines. And so if you look back at your formula up there, if you're trying to find side C, it's going to look like this. C squared equals A squared plus B squared minus 2AB cosine of C. So I need A and B, which I know, so let's just fill them in. A is 14.1. B is 18.2. And angle C is 60.4 degrees. And so I'm going to go to my calculator and I'm just going to type all that in. 14.1 squared plus 18.2 squared minus 2 times 14.1 times 18.2 times the cosine of 60.4 degrees. All right, and I get 276.54. So C is going to be the square root of 276.54, which is approximately 16.6 or so centimeters. So that would be the shorter side of the parallelogram that we found. So it's pretty straightforward. Even though it's an application problem, it's pretty straightforward use of law of cosines, because when you draw the diagonals in a parallelogram or any quadrilateral, you're basically splitting it into some triangles. So for example 3, directions are just to solve the triangle, and we're given 3 sides, no angles. So this is a case of side, 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 which falls into our use of law of cosines. So I need the angle formula. So I can start with any of them I want. So I might as well just start with A. And so remember, the formula, the way it was written at the top, says that A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of angle A. So that was the formula. So if I want to solve it for angle A, it's going to be A squared minus B squared minus C squared divided by negative 2 times B times C, and that's going to be cosine of A. So I can use this now to solve for angle A. And then I would have to do it to solve for one other angle. Actually, I could also use law of sines at that point. Once I get an angle, I'll have a side angle side case, and I could actually use law of sines if I prefer to. And then once I get the 2 angles, I could just use the 180-degree rule to find the third angle. So let's get one angle out of the way here. So if A is 26, so I have 26 squared minus 19 squared minus 15 squared divided by negative 2 times 19 times 15, and that's going to be cosine of angle A. So cosine of angle A is going to equal, and I'm going to put that in my calculator. So negative 0.1579, and then angle A will be the inverse cosine of that. So inverse cosine of it gives me 99, I'm going to round it off to the nearest degree, 99 degrees. So angle A, now we know is 99 degrees. Now that you've got that, here you have a little bit of option. So you can do another law of cosines and find either angle B or angle C, or you could do law of sines. So, that's just personal preference there. I think since we're doing law of cosines, I'll just stick with law of cosines right now, but you could easily set up 26 over the sine of angle A, 99, equals 19 over the sine of angle B, and solve it that way. But if I want to solve for angle B, so then I'm going to use the formula that was this. And then solving that, subtract over the A squared and the C squared and divide. And that would give me the cosine of B, and then I could find the angle B. So plugging in my sides again, 19 squared minus 26 squared minus 15 squared divided by negative 2 times 26 times 15. And I go to my calculator to get the value. 19 squared minus 26 squared minus 15 squared divided by negative 2 times 26 times 15. It gives me 0.6923. And then inverse cosine of that is going to be 46 degrees to the nearest degree. Okay. Should get the same thing if you did law of sines. So B now is 46 degrees. And then I don't need to worry about C. C is just going to be the sum of the two angles from 180. So, all right. And angle C, which is just going to be the difference of 180 and the two angles that we know. And 180 minus 199 and 45 is 145. 99 and 46 is 145. And that leaves the angle C having to be 35 degrees. I think I had 45 there. Okay, before we get to the next example, we need to address a few things. These are some of the applications you're going to deal with are navigation problems, which deal with direction. And we dealt with that a little bit in section 2.4. If you remember when we talked about bearings, you had some applications dealing with direction and bearing. And so remember, bearing is basically tells you how many degrees to the east or west of the north or south line that the ship or the airplane or whatever the object is traveling. So we're going to look at a different way of identifying direction, and that is with what we call the heading. And so it says in an earlier section, 2.4, we use bearing to give the position of one point from another and to give the direction of a moving object. So again, bearing is, how if I'm going 60 degrees east of north, it's off of the north line to the east or to the west of that north line, or east or west of the south line. Another way to specify the direction of a moving object is to use the heading. So what heading is always measured from the north line clockwise. So if this is north, however many degrees clockwise off of that north line that path is, that is the heading. And the heading is more formally, the heading of an object is the angle measured clockwise from due north, just like I said, to the vector representing the intended path of the object. So the intended path means that while the object, the ship or the airplane might be intending to travel along a certain path, certain variables may throw them off their path, such as wind speed or current, the water current. Those kind of things would make their actual path not necessarily the intended path. So they can change what their intention is. So it goes on to say that the figure below shows two vectors, referred to this figure down here, two vectors that represent the velocity of two ships. So one's traveling 14 miles per hour in the direction 120 degrees from due north. That's the heading. So you can see here's the due north line. So clockwise from due north, 120 degrees tells me that's the path of the first ship, and the 14 miles per hour is the rate. And so the vector, this is called vector, its direction is 120 degrees. That's the heading, and the magnitude is its rate, 14 miles per hour. All right. The other is traveling 12 miles per hour at 240 degrees from due north. So from due north, remember, we're always going clockwise. 240 degrees would put us around here, and then its rate is 12 miles per hour. To give the path of the ship traveling 14 miles per hour using the bearing method, we would say it is on a course of bearing. So if it's 240 degrees, if it is its heading, then think of this as the bearing would be 60 degrees west of, well, for the first ship it would be 60 degrees west of south, so we would write that as 60 degrees west of south. And for the other ship we would write that as, it's also 60 degrees, but 60 degrees east of south. So if you're given in bearing method, that would be how you would write those. All right, note that although a boat is headed in one direction, its actual path may be in a different direction because of the current of the river, or if you're referring to an airplane, airspeed. So the same thing can happen with the plane if the air currents are in a direction different than that of the plane. With headings, the angle is measured from due north to the intended path of the object. So that is kind of important there, meaning the path if it were not affected by the current or wind. The true course is the angle measured from due north to the actual path traveled by the object relative to the ground. So for an airplane, sometimes I refer to that as ground speed. If no exterior forces are present, so in other words, if there is no current, if there is no wind, then the heading and the actual path, the true course and the actual path would be the same. All right, so let's look at an example now that involves a navigational type problem or a directional problem. So this one, example 4, we have, we're dealing with planes. A plane is flying with an airspeed of 205 miles per hour with a heading of 105 degrees. So let's draw this out, because you really definitely need a picture or visual of this diagram to go by. So here's the north line. So this is north. So when it tells me that the plane is flying with an airspeed of 205 miles per hour with a heading of 105 degrees, so its intended path is 105 degrees. So when the 90's here, so it's a little bit past that. So we'll say this is 105 degrees. And that is its intended path. And with its airspeed being 205 miles per hour would give me the magnitude of that vector. So this vector is representing the intended path. The wind currents are running at a constant 35 miles per hour at 155 degrees clockwise from due north. So again, that would be just like the heading here. So as the plane is flying this way, you have the wind coming in a direction that is 155 degrees off the north line. So 155 degrees, let's say, is somewhere down here. You know what 180 looks like, so 155 degrees there. And so the wind speed is 35. I didn't draw that. It should have been a lot longer to represent the difference between. Matter of fact, let me just make that a little more. It doesn't have to be perfect, but that's really bad. So let's make this 205 look a little longer than 35. All right, so this angle was 105. Okay. All right, so what happens, so the plane is intending to fly in this direction, but the wind is acting on it in this direction, and so this is the resultant, this resultant vector is going to represent the actual path of the vector, of the plane. All right, and so what we want to know, the question is, find the true course and the ground speed of the plane. So not only do we want to find the speed or the rate of the plane, that's the ground speed, we want to find the course, like how many degrees, what is the heading of it. So we would want to find this angle there. So in other words, in order to do that, I'm going to need this angle, and then I would add that to 105 to get the. All right, so let's look at what we've got. So I have a triangle. That's an oblique triangle, which goes right along with our law of sines and cosines we can use. I have this side of the triangle and this side of the triangle. I'm trying to find the third side. At this point, I don't have this angle, I don't have this angle, and I don't have this angle. And right now, remember we said you have to have at least 3 parts to be able to use law of sines or cosines to be able to solve the triangle. Right now, I don't have that. So I'm going to have to back up and look at this and think of since this is what I'm trying to find, that means I'm not going to have this side. I'm not going to have all 3 sides, so it won't be a side case. So somehow I have to know an angle. And let's see what I know. Now I know the outside angle here, 105. I know this angle is 155. Somehow I have to be able to have another angle in this triangle. So I'm going to take you back to your geometry days on this. And so because these 2 lines are parallel, they're both north-south, this angle and this angle these are parallel lines, and this is a transversal. And so if you remember from geometry, remember your corresponding, your alternate interior, your same side interior, all those special kind of angles formed by parallel lines, and the transversal. So it's kind of like these two lines, it's transversal. These two angles are what we call same side interior angles. And if you remember, they are always supplementary. They always add up to 180. And that's going to be the case here. These are the parallel lines. This is the transversal. These two angles should be supplementary. They should add up to 180. In order to add up to 180, this angle must be 75 degrees. Now, what does that do for me? Well, this is what it does. So I know now that this is 75 and this is 155. And if I add those together, that would take me from here to here. 360 degrees goes all the way around. I can then figure out what this angle is. So if I know 155 plus 75, which is 230, and 360 minus that 230 gives me what's left here. And so that is 130 degrees. So this angle in here is 130. Now I can do a little more with this, because now I can solve this triangle. I have a case of side, angle, side. That allows me to solve for the other side. I can solve the triangle basically and find anything I need to. And so let me come out here and let's just look at the triangle and label it to make this a little easier, make a clean triangle out here without all the other lines. So this angle is 130, and this side is 205, and this side is 36, or 35. Oh, I got 30, that's a 5, I can't read my writing. And I am trying to find this side. So let's label this triangle A, B, C, just to make it easy. And so we're basically trying to find side C, first of all. All right, and so I'm going to go ahead and use my C squared equals A squared plus B squared minus 2 times A times B times the cosine of angle C. All right, fill it in. A is 35. B is 205. So minus 2 times 35 times 205 times the cosine of angle C. And I got my calculator now to find out what C squared is. And all right, and so 52,474.00. All right, so C is going to be the square root of that. 229.1. We'll just say 229 to keep in with the significant digits there. So 229 miles per hour. All right, and so the true course is going to be this entire angle. And like I said a minute ago, to get that entire angle, I know it's 105 from here to here. I need this little angle to add to the 105 to get the path, the true path. So I need to know angle A as well. Okay, and so technically, really, you could do one of the law of cosines or law of sines. So let's just do law of sines. It'll be a good refresher on that section too. So I know that now that I know what side C is, I know that 229 side C. So basically, this is what I'm doing. Side C over sine of angle C equals side A over sine of angle A. I know side A, I know angle A, and I know angle C. So I'll be able to find side C. So side C is 229. I know angle C is 130. Side A is 35, and angle A is what I'm trying to find. So that's my unknown. Okay, and then we can just cross multiply and solve this. So 229 times the sine of angle A equals 35 times the sine of 130. And then I would just need to divide by 229. And I would get the sine of A to be 35 times the sine of 130 divided by 229. All right, and that's what I get when I calculate that. And so then inverse sine to get the angle. So inverse sine of in degrees gives me 6.7 degrees. So let's go ahead and round that up to 7 degrees. So angle A would be 7 degrees. Now, that's not the answer though. The answer is 105 plus 7 degrees. So 112 degrees would be the bearing, would be the, I'm sorry, the heading. Would be the true. We're looking for the true course. All right, and the speed would be ground speed would be 229 miles per hour. All right, last example. So this time we're looking for the distance between two planes. This is what we know. They leave the airport at the same time. Let's just draw it out here. So they leave the airport at the same time. Their angle between their courses is 36 degrees. So let's make a 36-degree angle here. And so this is one plane. It's traveling 130 miles per hour, the other 150 miles per hour. And the question is, after 1.5 hours, how far apart would they be? So at some point they're traveling, one's traveling further than the other one. After 1.5 hours, we stop them, and we want this to represent the distance that they are apart. So what I need is the distance that they've traveled here. They don't give me that. They give me the rate or their speed. Okay, but remember, going back to just some more basic math, distance equals rate times time. We know that for any moving object. And so I can find their distance if I know the rate. So one plane was going 130 miles per hour for a time of 1.5 hours. The hours will cancel and I'll be in miles. So 130 times 1.5 is going to be 195. And the other plane was traveling at a rate of 150 miles per hour for a time of 1.5 hours. And that would give me their distance to be 225 miles traveled. So let's let the longer side here be the 225 and the shorter side be this guy's got 195. So basically I am trying to find, let's label this A, B, C, trying to find side C. All right, and this then becomes just a very basic law of cosines problem. Trying to find side C. And we know side A, we know side B, we know angle C. We've got everything we need. So this is going to be a pretty straightforward. So the C squared equals A squared plus B squared minus 2AB cosine C formula. That's what I want to use. And filling in what I know. A is 195. B is 225. All right, times the cosine of the angle C, which was 36 degrees. And then again, I'm just going to put that in my calculator. And I get 17,658.76. And okay, of course that's a big number. I've got to take the square root of that though. All right, I get 132.8 or 0.9. Let's just go say, let's keep significant digits here. So let's say 133. So the distance that they are apart after 1.5 hours would be 133 miles.